Now we take what we have learned about the mixing of atomic orbitals to form molecular orbitals to look at the energy levels of some very simple molecules. We begin with homonuclear diatomic molecules, for example fluorine and oxygen, in which the orbitals are simple combinations of either atomic S states or atomic P states. In other words, F2 and O2 are molecules in which there is no sp hybridization. So in this case, we can construct quite simply the sigma and pi states for the molecule. So the going to the two S states, these then hybridize into two sigma orbitals with cylindrical symmetry again. So the sigma 2s and the corresponding antibonding sigma 2s star. The p states hybridize into the sigma 2p states, so these were the pz states, and the sigma star 2p antibonding state. These have the largest split because of the strong interactions between the orbitals when they interact end to end. The side-to-side interactions that come from the px and py state give a smaller split between the antibonding and the bonding states, which I'm showing schematically here. Remember, these are lying in two orthogonal directions by degenerate energy levels. So, this is how we expect the simplest energy level scheme to be in the case of a simple diatomic molecule, once again with no sp hybridization. Let's take a look at filling these states up for the case of O2. Oxygen, which has 8 electrons, has 2 of them in the 1s2 states, and therefore we have a total of 6 electrons from each oxygen atom for a total of 12 on the molecule. So let's fill up these states then with 12 electrons starting from the lowest energy levels. Then I'm going to have to draw them here, I guess. And so now we have got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 2 more to put into the next orbital in energy, which are these pi antibonding states. Hund's rule tells us that to minimize electron-electron interactions, we can put them in the same spin orientation into the pi star x and pi star y orbitals. Note that the molecule is still bonded because we have 1, 2, 3, 4, 5, 6 electrons whose energy has been lowered relative to the 2 p states on the atoms, and this generates the bonding energy for the molecule. So these electrons here of increased energy still allow the molecule to form a stable bond. However, they do have a very interesting property. Because they correspond to a pair of unpaired spins, they can be lined up easily in a magnetic field, with the result that molecular oxygen is paramagnetic. And some of you may have seen the demonstration in a freshman chemistry class of pouring liquid oxygen onto the poles of a powerful magnet, where it sticks because of the induced magnetic dipole in the molecular oxygen. So this was the simplest case of no sp hybridization. Many other diatomic molecules from the same region of the periodic table do hybridize. Carbon, of course, is the famous example, but also boron and nitrogen. The result of this hybridization is to invert the position of the sigma 2p and the pi x and pi y bonding orbitals. So note on this diagram on the slide that this orbital here is the sigma 2p, and this lower lying orbital here are the pi x and pi y orbitals. So that is the picture of the simplest types of homonuclear molecules. What about some of the heteronuclear molecules? Well, in this case, the formation of molecular orbitals and the filling of those orbitals is complicated by the fact that now the partners in the bonding have different energies, and therefore the orbitals that are formed have a different character. So the example I give on this slide is hydrogen fluoride. Fluorine has 9 electrons, 2 of which are in the 1s2 states. This then leaves 7 valence electrons on fluorine. Hydrogen in its s state then contributes to these valence interactions. So here is the 1s state of hydrogen, and it hybridizes with the p, x, y, and z states of fluorine. There are 7 electrons in fluorine now in the 2 p states and 2 s states, and 1 from hydrogen, giving you a total of 8 electrons. The result then is that electrons transfer from the hydrogen into these new compound orbitals. These 2 orbitals here are called the sigma 1 and sigma 2 orbitals. They come from the hybridization of the 2s state on fluorine with the 1s state on hydrogen. The corresponding hybridization of the p orbitals with the s orbital on hydrogen produces the sigma 2 state. And finally, one has unfilled or unhybridized p states left on the fluorine, each of which are occupied by 2 electrons. These are referred to here as X or non-bonding orbitals because the energy of the electrons is not affected. The overall bonding interaction comes from the strong charge transfer between the hydrogen and the fluorine, resulting in a very polar molecule. These states here correspond to the lone pairs of electrons that we drew in the Lewis structure.